All right, so let's continue here with section 4.3, and let's look at an application of these rules of derivatives that we have covered in 4.3, specifically for exponential functions. All right, so let's look at a business application known as consumer expenditure. Let d of p here, d of little p, represent our demand function. Recall we talked about the demand function before. Let's define it as d of p. So let d of p be the consumer demand function, all right, at price p. In other words, d of p here is representing the amount the consumers will demand of an item, or how many units consumers are willing to buy of an item at a certain price point p. Okay. Well, if d of p is our consumer demand function, then the consumer expenditure function is defined as follows. Let me capitalize this. Just to emphasize that we're focusing on this type of function, consumer exponential function. The consumer exponential function is defined as E of P equal to P times D of P. The price that we set this unit, that we set our item at, times the demand for that item. In other words, this exponential function represents how much we believe consumers are going to spend at this price point based on the amount of demand for that item at that price point. Okay, so how much consumers are going to be willing to spend at a certain price point for a certain price and demand of that item. And what we want to do here is we want to, when it comes to consumer expenditure, companies want to maximize that amount. They want to maximize how much individuals are willing to spend, correct? When it comes to businesses. So let's look at an example here. Suppose we want to find a price that maximizes consumer expenditure if our consumer demand function is as follows. Suppose our consumer demand function, D of P, is defined as D of P equals, D of P equals, let's do 5,000 times E to the negative 0.01 P. So that's the demand function. The amount of items that the consumers are willing to buy, the amount of units that consumers are willing to buy at a certain price point is defined by this exponential demand function. Okay? So if we want to maximize, there we see that keyword maximize. If we want to maximize, if we want to optimize consumer expenditure, the first thing we have to do is find the function that we're trying to maximize. What are we trying to maximize? Consumer expenditure. How do we define expenditure? E of P equals P times D of P. We're not trying to optimize the demand, we're trying to optimize the expenditure value, the expenditure function, not the demand function. But we can use our given demand function here to find E of P. So the first step for this type of problem is to define your expenditure function, your E of P. All right, so looking at what we have above, to define E of P, we take P, where P is just some unknown price value, multiply by our demand function, D of P. Okay, so we're going to take P times 5,000, E, 5,000 E to negative 0.01 P. Really can't do anything else with this, anything else much with this, so let's just leave it as it is. So our exponential function E of P is going to equal P times, we'll move 5,000. No, I'll keep it in front. P times 5,000 e to negative 0.01 p. Okay, so this is the function that we want to maximize. This is the e of p, the exponential function that we wish to maximize. So now that we have defined e of p, the second step, let's maximize that function. Let's maximize e of p. Okay, and how do we maximize the function? How do we optimize the function? What's the first step that we have to do in order to optimize a certain function? We have to find its derivative. So first step, I'll call that I. Let's find the derivative, e prime, of this exponential function. Okay? So again, our equation here is e of p equals p times 5,000 e to the negative 0.01 p. Okay, so how are we going to go about finding the derivative of this function here? Okay, well, here we have a function of p. Right, our exponential function is a function of p. And what do we have within this function? Two other functions of p multiplying one another. Which means then, to find the derivative of this expenditure, since we have a function of p multiplying another function of p, we have to use the product rule. So let's do this on the side here. So let's define f, and let's define g. F in this case will be our first function of p, which is just p. And then g will be our exponential part. So g will be 5,000 e to the negative 0.01 p. All right, and then we find the derivative of each function. So f prime with the derivative of p with respect to itself. The derivative of just a variable with a coefficient of 1 is just 1. So the derivative of p is just 1. All right. And then g prime, well, how would we find g prime here? Using the rule for exponential. Again, how do we define the derivative of the exponential function? The derivative of e raised to some function is that same exponential multiplied by the derivative of the exponents. So here you're going to take, and again, 5,000 is just a constant coefficient up front, so that doesn't really matter. So we're going to take 5,000, then multiply by the derivative, our exponential part here, of our exponential factor function, which would be itself e to negative 0.01 p, but then times the derivative of the exponent. And the derivative of the exponent here will be, well, let's see, what's the derivative of negative 0.01 p? Well, if p is the first power, and this is the coefficient of this term, of this variable, then the derivative of negative 0.01 p is just negative 0.01. Okay, and then multiplying the coefficients, 5,000 times negative 0.01, 5,000 times negative 0.01 gives us negative 50. So negative 50 times e to negative 0.01 p. Okay, so now let's apply the chain rule here. Let me move this a bit. So now let's apply the chain rule e prime of p. So again, using the chain rule, we take f prime times g. So 1 times g, where g was 5,000, e to negative 0.01 p, plus f times g prime, where f was p, and then g prime here we found to be negative 50 e to negative 0.01 p. Okay, so in other words, we get 5,000 e to negative 0.01 p minus 50 p e to negative 0.01 p. All right, I just want that coefficient negative 50 to the front of these two factors. Okay, but let's see if there's something else we can do here to help us out. Since again, we're going to be trying to optimize this function, then you know what the next step will be. We call it to optimize a function, we find its derivative, And then once we find the derivative, we then gotta find its critical numbers. Meaning we need to solve for the zeros of this function that we have. So let's see if we can rewrite this, if we can factor anything out to make that process a bit easier. Let's look at these two terms. What do these two terms have in common? Well, 5,000, negative 50, those are going to have a common factor of, of negative 50. Or let's bring out positive 50. Okay, so these two have a common factor of 50. 5,000 and negative 50 have a common factor of 50. So let's pull out the 50 here. Okay, but let's look at what else they have in common. What else do these two terms have in common? Notice these two terms also have a e to negative 0.01 p in common. So let's factor that out as well. So let's pull out an e to negative 0.01 p. And what are we left on the inside now? Just want to double check everything's going correctly. So if we take it out 50 from 5,000, pretty much essentially divided by 50, 5,000 divided by 50 leaves us with 100 in that first term. Okay, we pulled out a 50 from 5,000, leaving us with 100, and then we pulled out this entire exponential to the front, so we just left with this constant of 100. Minus, we pulled out a 50 from this second term, so we're left with just a coefficient of 1. And then we also pulled out this exponential from the second term, leaving us with minus 1 times p. What's left on the inside, which is just p. So this is going to be our derivative. 50 times e to negative 0.01 p times 100 minus p. Okay? So we found the derivative. And now for the second step, well, what do we do to optimize the function after we find the derivative? Set equal to 0 and solve for p. So next step, set our derivative equal to 0. And in this case, solve for our variable of p to find the critical numbers of our price point. Okay, so we're going to take 50, what we found, 50 times e to negative 0.01 p, multiplied by 100 minus p, and set this equal to 0. Now, the reason why I put parentheses around the first term, around this first here factor, is because, again, the critical numbers are any values of p that will make your equation 0. And to solve for those values of p, we got to set each factor that involves p equal to 0. So you're going to have two equations. We're going to set this first factor of p of 50e to negative 0.01 p, set that equal to 0, and then set the second factor of p, in which we have 100 minus p, and also set that equal to 0. Well, let's solve the second equation here, but there's a much more easier one. So 100 minus p equals 0, using algebra to solve for p, we get that p is going to equal 100, right? Add 100, so try 100 from both sides. We can have negative p equal negative 100, divide by negative 1, gives us 100 for p here. But what about this other equation here? We want to solve for p. Well, what we can do, divide both sides by 50 first. So that's going to give us e to negative 0.01 p. All right, e to negative 0.01 p, divided both sides by 50, 0 divided by 50, that is still 0. Okay, but then again, we have this p in the exponent. What are we trying to solve for? We're trying to solve for p. So since our variable of interest is in the exponent, what should we do? How can we bring this p down? natural log. We can take the natural log of both sides. So the natural log, taking the natural log of both sides, pretty much essentially cancels out this ln and e, leaving us with negative 0.01p equal to the natural log of 0. Hold up, ln of 0. What is the natural log of 0? Let's find out using our calculators. Natural log of 0 is equal to non-existent. It does not exist. Okay, remember, for properties of natural log, for natural log function, the inside has to be positive. It has to be greater than 0. So in this case, the second part here, this does not exist. So there is no equation, there's no value of p that will make this equation 0. Okay, so we have none in this case. So our only critical number is this value of 100 from 100 minus p. Okay, so that's our only critical number. All right, and if we want, and in this case, we just wanted to find the price, so this will be our answer. To maximize consumer expenditure, they will have to set their price point at $100. Now, if we wanted to find the actual maximum value, if we wanted to find the maximum expenditure value, let's see if we can fit in this line here. I'll call this number 3. If we want to find the maximum value, if we want to find the maximum consumer expenditure, then what do? After we find our critical number of the function we're trying to optimize, how do we find that optimal value? By plugging that critical number back into the original equation that we're optimizing. Okay, meaning we're going to evaluate our exponential function at p equals 100. All right, so we're going to take our exponential function of e and evaluate it at 100, where 100, again, was our critical number. Okay, so then plug in 100 into E of P. Again, E of P would define as P times 5,000 E to the negative 0.01 times P. So you're going to have 100 times 5,000 E to negative 0.01 times 100 to give us approximately, let's see, let's use our calculator to find this answer. All right, so I'm going to take, again, to find the actual maximum value of this consumer expenditure, we're taking the critical number that we found and plugging it back into the original function of E of P. So 100 times 5,000 times E to the negative 0.01 times 100. So I'm going to take 100 times 5,000, second ln for E, and then for E, we're going to have negative, and don't forget, this is the negative sign. This is the minus sign here on the right column. This is the negative sign here in the last row. And make sure to use that negative sign in this case. Negative 0.01 times P, which was 100, to give us a maximum expenditure of $183,939.72. Round to the nearest cents. So we're talking about money here. So this is going to maximize at a value. Our consumer expenditure is going to maximize, or let me rephrase that, at this price point $100. If we set the price to $100 here, then our maximum consumer expenditure is going to equal $183,939.72. $83,939. $1.72. So that's how much consumers are willing to spend on this item based on this price point and based on this demand. All right. So again, not too different from the process that we saw in chapter 3 when it comes to maximizing or minimizing a function. The process is the same, except that in this case, we first got to define our expenditure function, which is defined as P times D of P. And once we define that function, then the steps that we take are those similar to what we saw in 3.4 and 3.6. Find the derivative, set the rate equal to 0, solve for our critical number, which will be our optimal point. And to define the actual maximum or minimum value, we take that optimal point and plug into the original equation that we're trying to optimize. All right, and that concludes here section 4.3 and chapter 4. Oops.